Yeah, so I'm a computer science AI person, roboticist, engineer, right? So everything I'm saying from that perspective, right? And for me, I'm excited about robots and robots that can accomplish human scale everyday manipulation tasks. And a robot for me is an electromechanical device that is articulated, right? That has a program. The program moves the body motions generate forces, and the forces change the environment. And by kind of putting the forces on the environment, the robot can perform tasks, right? And so from my point of view, the world is pretty simple. So the key problem we should all focus on is the body motion problem, right? So we are giving the robot a task request, and the control program of the robot has to figure out a body motion that achieves the desired effects and avoids unwanted side effects, right? And that is all there is that we have to do. And that's kind of a very challenging task, right? Because an underdetermined manipulation task might be something like set the table, and we want all the motions that are necessary for getting all the objects from the places where they are to the place and to the arrangement that basically makes the goal. And so what makes that problem so challenging is, so if you're looking at that very context-specific body motion that you need for opening, closing container, grasping everything in the right way, and that very vague task request like set the table, the whole difference has to be in the knowledge and the reasoning of the robot, right? So there can be no other place. But now imagine a program that has such an amount of knowledge and reasoning power to do that task, right? And that's not all, right? If we are looking at humans, it's not only that we are solving the body motion problem, but we also understand what we are doing. We know why we are doing it, how we are doing it, what we intend to do, what the effects of our actions most likely will be, how to achieve specific events, how to avoid them. We all even know things like, what can I not do, right? And where do I need help? And why can I do what is missing in order to accomplish that kind of thing? And the big thing is, we are also capable of taking that understanding and make it actionable, right? So we can transform that into the body motion that then robustly and flexibly solve all the tasks, right? So in the case of ChatGPT or something like that, well, it can certainly answer all these questions, right? But whether kind of it can make these answers actionable in a program and kind of implement the consequences of that knowledge, I think is still an open question. Yeah, so one obvious approach for solving the problem is the generative AI approach, right? And the idea is we are simply looking at the whole thing as a huge probability distribution over tasks and all possible contexts and motions, right? And the contexts are not directly accessible, so we take all the images we have, the language, and now we are including videos. And we are learning a huge probability distribution over all these data, and in a very in a space that includes very kind of low-level features, right? And I think there are some lessons that we are learning that make this approach extremely powerful, and this is the central role of language, right? And I think one reason that these systems are so enormously powerful is that anything about anything that is relevant about solving in the problem is somehow in some text, right? Because that is communicated by one person to another person, And that makes kind of the knowledge very dense. And so the idea that at least some of the people have is that the language is sufficient to actually link everything together. The other thing is, well, we are taking that in a huge space of experience, right? So we are looking at all the tasks and motions that are successful, and we go to the infinity with that, and I think again. So for one thing, it's amazing that you can learn a probability distribution over spaces that are so huge, right? And even more impressive is if you are looking at that thing as a kind of a conditional probability, right? So you're retrieving the argmax over all motions that are there for a certain task you want to accomplish under certain conditions. It's amazing if you are prompting in the right way, what kind of detailed answers you get, right? So it's extremely powerful. But it also has its limitations because it's it's a joint probability distribution, so it's kind of merging different things at a feature space. It's not clear if a solution that it's generating is really feasible. And and the question is how far we can get. So the research hypothesis I have in that talk is that we are actually taking that approach, generative AI, and we kind of combine generative AI with digital mental models. We get another boost in cognitive capability. And for that, we actually have to kind of bring together the science and engineering that we have in robotics and the machine learning kind of insights and actually bring it together as one field. And I would call it either AI-powered and cognition-enabled robotics, right? So the power comes from the data and the huge kind of way of making a huge scope of intelligence. And cognition-enabled is what you actually can infer in terms of understanding, assessment, gaps, and both come together. Another way of looking at it, that we want to have a data-driven science and engineering of robotics, right? So we want to get the best of the two worlds. And so I think what we need, if we, in particular, if we are thinking as engineers, is we want models, right? And so that is what we are basically taught from the first day being at the university. And I think we all know how important models are and how powerful they are. And there are kind of different views, right? So if we are looking in cognitive psychology or philosophy, there is Craig's hypothesis of the nature of thought as maybe kind of one of the earliest very concrete ideas here. So if an organism carries a small-scale model of the external reality and of its own possible action within its head, it's able to try out various alternatives, conclude which is the best of them, react to future situations before they arise, utilize knowledge of past events, and react kind of very flexibly and robust, right, to everything opposed. So again, so if we are comparing to generative AI, here it's actually, we are talking about structures in the head, and that actually the input-output of these generative AI systems are grounded in models, right? And we have the same idea in computer science, right? When you are entering your computer science class, and in the very first lesson, the first thing you are told is that a computer program is not only something that specifies the computations inside the computer, but it communicates the idea how a problem is solved to the programmer, right? And for that purpose, we have data abstractions, we have control abstractions, and we are taught to design our programs well, so that kind of programmers can look at them, change them if the requirements change, and they can live over a long time, right? And we do that kind of for our programs, right? But this is something that generative AI systems don't do yet. Or if you're taking the first lesson in artificial intelligence, right? So what you are taught is that problem solving is reasoning about representations of models, right? So you're making a model of the world. You're trying to make that model explicit, represented on a syntactical level. And then you have formal reasoning mechanisms that only work on a syntactic level. But if we are looking in first order logic, we can ensure that this reasoning is, for many cases, correct and complete, and it kind of provides explanations and everything else. Okay, and this is actually, so when we put models in the head of robots, right? So you can see that the robot is doing manipulation tasks. It's the same program, right? And it's just that the models we change. So it's acting in different environments, it's different robots, different tasks, and the same program, and it works, right? So transferability in a model-based world is easy, right? Because you simply exchange the model of one robot through the model of another one, and the rest is in the inference mechanisms, right? The same for environments and something like that, right? And this is kind of the game we want to play. So if we look at these models, right? So if I've already said what I think a robot is. So this is actually the conceptual framework over which the models should be built. So we have robot agents that decide how to act in the world in order to accomplish the task. They have some software, which is a control program, which is interpreted. The interpretation kind of moves the body of the robot. The body motion generates forces in the environment, and we have perception that looks at the state of the environment, gives information to the agent, and the changes in the environment should be such that the task that the robot gets satisfied, right? And if we want to have a robot that is competently acting in the world, and then it has to have such kind of model inside and reason about it. Right? And yeah, so the game that I want to play in that talk is that we are taking such a model, and I try to explain how we go about getting such a model in the head of a robot. So we have that model, I call it a digital mental model. We have a system which is essentially a question answering system like a Siri agent. And essentially we can tell the system, make a kind of a model of the task, set the table, right? And then we can ask queries about the models, and we get the answers, and by interacting that, we basically have seen that we can accomplish these tasks in a fairly reasonable manner. So I will first look at what is the model of the control program and the interpretation here. So the way we do that is that we believe that and I have heard these ideas here today from different people, that the world is actually or a large part of the world can be understood through schemas, through manifolds or structures that make our life easier. Right? And so one of the things that should exploit that structure are generalized action plans. So a basic assumption that we make is that for action verbs like pick and place, cut, pour, wipe, we can actually find generalized action plans that explicitly represent the schemas underlying the action. And the same is true for the motion level, right? And because we want to represent that in a very generalized manner, we know that everything is highly context dependent, so we have to provide universally unquantified knowledge that we can use in order to contextualize these schema tasks for the specific tasks at hand. So let's look at the different components that were at work when we have seen the robot doing the task. So the first is the generalized action plan. So for fetch and place, the generalized plan simply says, if you want to get an object, any object, to any destination, right? So what you have to do is you have to be with the robot at a location where the object is visible and reachable. And at that location, you perform an action, namely fetching the object. And a similar thing you do at the destination, right? So where the location where destination is visible and reachable, I perform the action placing the object where it should be, right? So there's a lot of hand waving in there. And we will see how we resolve that. And the motion plan is similar, right? So we are taking models of cognitive psychology of action, like the Flanagan model that structured the pick and place behavior into schemas using phases: reach, lift, transport, release. Each of these phases has goals, which are force dynamic events. And we are refining that because we are not cognitive psychologists, but we are roboticists who want to get it running in the robot system. That means we simply have to go at more detail and basically look more systematically what are all these parameters, so that if we specify a program, it would be actually sufficient to generate the detailed behavior. And that's basically the schema we are using, and these are the parameters that we need. So the next component is the knowledge that we have to provide the robot with, right? So it has the general plans, but now we are providing the robot with knowledge chunks, with knowledge such as cups used for table settings have to be clean and unused. Cups in the cupboard are clean. Cups have to be grasped from the outside. You have to parameterize motions to avoid unwanted side effects. Spilling is an unwanted side effect of pouring. The pose of pickup, that is something that can be learned from experience. But the power of these knowledge chunks are that they are universally quantified, right? They hold even for objects the robot doesn't know yet, right? So it's actually helping the robot to scale towards open environments. And they are also composable. And they are usable in different contexts, right? If I know that cups in the cupboard are clean, I can use that knowledge to get a clean cup. but I also can use the knowledge when I unload the dishwasher in order to decide where I should put the clean cup, right? So the multiple use is also a very important component. And now we are coming at the heart of the system, how it actually works. So we are giving the systems underdetermined action descriptions, like an action of picking up a cup from the kitchen table, and bringing it to the kitchen table. Right? So what our system is doing, it's for those tasks, it's basically fetching the generalized plan and then extending the generalized plan with the parameters of the corresponding motion plan, right? And once it does it, it simply has to ask, what are the parameters of my motion plan that make that action successful, right? And this is actually the critical inference task that a robot has to solve. And here we see, for example, what is happening if the robot picks up the milk box from the fridge, right? So it knows that milk is an item that has to be stored at a cold place. So fridge is likely. Then it's basically where in the fridge, it's on the shelf of the door. It infers the handle, and it infers the articulation model of the handle, right? And these are essentially kind of the specification for the vision system and the constraints for the motion control system to derive the concrete action to get the milk box out of the fridge. Okay, that brings us to the question, so if this is a game, right? Then I think the most important problem that we have is if we are looking at the context of tasks. The context can be anything, right? And it can be very detailed. And the question is, how can we actually represent the knowledge that we need in order to make these context-specific refinements, right? And the question is, if we are coming from the AI point of view, from the classical AI point of view, and you want to have something like a symbolic knowledge base, can we think of a knowledge base in which we kind of have the context information available that we need for the specialization of motions and all the ones that we need? And the answer is, of course, yes, right? And we see that in particular in the computer games, right? If we are looking at a computer game at a virtual reality environment, we see that we can build the environments in a photorealistic way with realistic simulation, and it's a data structure, right? So we have it in our hand. The only thing is we have to turn it into a symbolic knowledge base, right? So this is why we actually made a photorealistic model of our lab environment, right? So this is the scene graph data structure. And you see, it's a professional job, but you also see that inside that environment, the model of our robot with our control program running on the real robot is also working in the simulated environment. And we are trying to get more environments at that level. Environment is very detailed, something like bread pieces. We also look at how to represent these objects during cutting, during pouring, and how we can reason about that. And that is possible because of the scene graph data. So that shows you can generate everything out of a symbolic knowledge base, right? That's also trivial because the geometric information is in the scene graph, but now you can ask your semantic question, and it's actually grounded answers based on your environment, right? And you can basically take all the knowledge and build a knowledge service where you have the kind of experiments recorded and you make them accessible. So that's essentially the data, and we can have robots that are building these kinds of models automatically, at least for limited environments like retail stores. Okay. So the big thing is, this is a logical formula, right? So it's a scene graph data structure, but you can basically, when you have a symbolic predicate like on, you can compute it out of the scene graph data structure, because if you have on AB, you take the object A, you take the object B, look at their positions in the scene graph, whether they are in contact. You even can delete the object B and can see whether the object A falls, right? So that's kind of how you can build up your symbolic knowledge base on the scene graph, right? And the cool thing is, your symbolic knowledge base, you only construct in a lazy manner. You only have to construct the part of the symbols that you need to answer the query that the system is asking, and all the others you can leave as scene graph data structures, right? And we know scene graph data structures can be maintained in real time. Oh yeah, please.
Sorry, I didn't want to interrupt. I'm just curious now, because it seems like you're building up your environment based on this knowledge base through the construction of the scene graph. Now, but like in like everyday environments, what we kind of want to do is to go the other way around, right?
Yeah.
So we see our environment, build a representation. Is that transferable? Is that still possible with that system?
No. So I think so this is kind of one step in it, right? So I make the assumption, well, I give the scene graph as a data structure as a given, and now I see, can I get a working robot control program based on that, right? And the second question is, can I get actually the scene graphs, right? But if you're seeing currently the generative AI methods, right? So it's kind of, I have no doubts that you can then learn a system image in, scene graph out, right? In particular, this is the way that the system are trained anyway, right? So it's, and if you have the scene graph data structure, you have it. It's just decomposing the problem, but my goal would be exactly the same. Robots go in an environment, actually construct the scene graph, but the scene graph could automatically be used as a symbolic knowledge base. Yeah.
And now you just basically start from the scene graph and leave that for future work. But your DMM would still work on.
Yeah. Also, I think if you think about it, right? So scene graphs have representations for the same things in multiple sub-scene graphs, right? So you can have a state where the object is unknown, then you can get refinements, you can even get learning about objects on the fly in that framework, right? And it wouldn't hurt in any way. Okay, so and this is essentially the data structure, and it's a very model-like data structure. It's a hierarchical graph. It contains essentially all the components of our model that I have presented, and we have also abstractions like material, texture, and the geometric form, and it's composable, right? Because it's actually the universal scene description is made for describing all environments this way. And yeah, because of what I've said, it's also at the same time a symbolic. So the only thing that is missing from a scene graph in order to get a full-fledged knowledge base is the class label of the nodes, right? So this, in a standard scene graph, it would not know that a node is actually of category refrigerator. So that, again, the first thing would be is to edit it by hand as an attribute, but you can also think of just the object recognition system, just render the node and run YOLO on it and let it actually tell the category, right? So I think it's kind of, yeah, very, very fine that. We can also do that on dynamic structures like images, right? So we can have a predicate like the expected image, right? That takes the pose of the camera and the current belief about the environment and say, this is a picture that I expect to see given my belief about the environment. So we can even support rounding of symbolic expressions. So if we tell our renderer to color every object in a different color, we can simply say what object is at that pixel by looking at the color, right? And use the color coding. Or we could say any object in the scene, but our milk carton is invisible. And we get a perfect segmentation of the milk carton that the system could use for, again, as a prior for object detection. And we can also click on anything here, and anything would have a definition in an ontology, and you would have knowledge about that, right? And because it's in ontology, and you know this is a cup is a container can contain fluid substances and stuff like that. We can use the ontology to link what is running on the robot and actionable with knowledge graphs we learn in the World Wide Web, right? By just connecting the classes we have in the knowledge graphs to the classes we have in our ontology, and thereby we make these things in the knowledge graphs actionable in the robots. And yeah, and this is not only working for static situations, but it's working for any action that is happening in a scene graph, right? So we have here Andre basically doing table setting tasks, but we have the simulator instrumented, so it detects force dynamic events. So already at execution time, we can get semantic queries about the actions that are taking place, and kind of the data are segmented and in a ground truth manner, right? Because we have actually the events in the physics simulator available for detecting something like contact hand object and something like that. And now we get all the semantics again. And just at the end, there's another part. So now we basically want to collect the data, right? And here we take models of cognitive psychology, automatically pass them in that, and now we can ask questions, get the training data for learning problems. But the thing is, if we collect these data in such a comprehensive manner in these environments, right? So we can basically afterwards provide the data for any learning tasks that we have, right? Because we have recorded all the data. And we don't want to do that only for actions that we have in the virtual reality environment, we basically take the same techniques in order to have it running on the perception systems of the robot, to interpret videos in the web, and the game is again the same one. So we want to see an action observation. We are animating this action in the scene graph using the physics simulation as kind of a mechanism enforcing consistency. And by having that, we can make sense out of what we are seeing, right? And here you see kind of how that can be used for imitation learning. And yeah, and the avatar we are seeing here is an avatar in the virtual environment. So the human has to stand on the floor in order not to fall down, and the system is ensuring these kind of things. Yeah, and here you see also kind of imitation learning to a very different body by just taking these data. Okay, so this is actually the information, and this is then what you can do in the robot control system, right? So we can have, again, logic expressions. We can say a robot R can accomplish task T in environment E through motion M. If, in our specific case, the task is to open a container, and we know the articulation, we know the kind of joint and the part relationship, and then we take that in order to compose motion constraints for a constraint and optimization-based controller, right? And the predicate can execute robot M is true if the constraint and optimization-based controller is actually computing the motion M for these constraints and the respective objectives that I have, right? And by that, we have in our robot control system a very compact knowledge piece, but that behavior that it generates is actually the result of the research in robotics, and you compute it with methods that are kind of, yeah, the motions are guaranteed to be collision-free, and they are then also typically optimal, right? Okay, so now we basically have these, the belief state, these digital mental models, and they are very detailed and accurate models of real-world scenarios, right? But now we can also use these digital mental models and build research laboratories out of it, right? So there's no need that these mental models should only run in the head of the robot, but we can have them as research infrastructure and make them available as Docker containers, and researchers can simply use them in order to perform tasks. So here we are taking the same technology, we are kind of building a whole research building. We have our simulation running in there, and this is actually one laboratory. It's running as Docker containers. I will show you that in a second. And you see the same kind of behavior, that the same control program is running here. And you're going into another lab. This is a lab where you learn knowledge from the World Wide Web. In this particular case, you are learning from biology books of fruits, and WikiHow pages on cutting. And the question is how to perform cutting or kind of halving, watering, peeling of any fruit for any purpose using any tool, right? And the idea is here you learn a knowledge graph by basically taking the web resources. You are using the generalized plans in order to see whether the plans that come out are feasible, and then to execute it in reality. This is kind of another environment. This is kind of the environment in presence, right? So there you can use the virtual reality classes of Meta, and you can go and interact with the environment. And so any place in the world, a student could interactively work with the robots in that environment, right? And yeah, and you can do that too, right? So you can visit the virtual research lab. You can go the object transportation lab. You can choose an environment, you can choose a robot, and choose a task, and you can run it as a Docker environment, right? The idea is that any researcher at any place actually has access to our research software and can run it. Yeah. It should simply make it easy to get a head start with the environment, right? And do that. And then if researchers see that kind of the things are doing what they want to do, they should take the software, download them, and run them on their own. But the thing is that you first want to get an easy access to the control software so that they can check before they have to do the work, right? And you see again when it's starting, so the first Edorum it's a bit slower, and also the Tiago is not as optimized as the PR2. So it's kind of looking for handles and poses. It's kind of just thinking about how it's opening the door. Yeah. Okay. Yes. So that's that. Yeah. The same environment also, it's a kind of that virtual research building is actually supposed to be kind of an environment where we get talents and students in, even high school students, and where we basically can conduct leading edge research, and where we also can do the outreach so that either kind of companies have access to the technology, or the general public can play around in virtual environment and see what it means to have a robot, household robot that is actually doing these kind of things. And so another thing we are doing is so in that we are building an interactive textbook for AI-powered and cognition-enabled robotics. In the textbook, you can kind of go and make exercises in the research lab as a student, so you can deepen your understanding in the textbook by doing that. And the environment also has other components like competition arenas for RoboCup at home. we're trying to get them going. And as I said later, we would also like to have innovation and transfer. Yeah. And yeah, so that's kind of that part. Yeah, so just two final thoughts. So for one thing, I think at the moment, with that huge hype on generative AI and robotics, I think there's kind of a question of what is the place of robotics? How will robotics actually in future kind of work together with generative AI? What is actually happening to the insights, results robotics has generated? And I believe that we will see something like data-driven science and engineering of robotics. And so there's Stephen Brandon. He actually combines physics-inspired reasoning with those. And I think the people in physics have a very good kind of take on how kind of these science and engineering fields and the generative AI can be synergetically combined, right? And one of the ideas I took from Stephen Brandon is that if you are looking at these generative AI systems, right, and like systems like the autoencoders, and we see the representation and the parameter layers there, there's nothing that prevents us from actually plugging complete systems, formulas, models, systems in that representation layer, right? If we are doing that, we actually have systems with guaranteed properties. We have our explicit representations in the heart of generative AI system. And I think this is for us a very cool way to actually seek the synergies between robotics and generative AI. And for us, I think it works for explicit knowledge representation and reasoning, where kind of in knowledge representation and reasoning, you typically have to choose an abstraction beforehand, which is fairly abstract, and then you have to live with the discretization, right? But in the context of a generative AI system, the system could actually learn to map the real world onto those discretization. It could choose different discretizations depending on the context. So I think this could be a lot better, right? On the other hand, it's clear if we have these kind of generative AI techniques that we also have the techniques to take abstract output of symbolic reasoning systems and convert them in real robot kind of motions and perceptions, right? So I think it's at least kind of something that is worth of exploring, whether actually that could work and whether that would to lead to it. The other thing I would just want to mention, right, so there's, if we are going with these very detailed models, right, and we I mean, the game that I have played when I controlled the robot is that I made the robot believe that it's acting in the simulated world, right, with all the ground truth knowledge, but in reality, it's acting in the real world, right? So I think one might think that this is a disaster because of the sim to real gap, right? But it isn't, right? It's a hard problem because yes, so the robot makes many failures because its model is wrong, but it's a digital twin infrastructure. It updates essentially its model in every cycle. The reality is basically telling the robot how to change the environment. It's a different game that the people in generative AI are playing when they use these data to learn something, because we are using these models in the feedback loop, right? And we are constantly updating. We are paying for that in a heavy price. So about 85% of the code of our robot is failure detection, failure diagnosis, failure recovery. But the information that is contained in these models is so valuable that it fully pays off, because it's simply a very good information basis for making the right decision. So that's kind of what we are trying. Okay, so that was it. So thanks a lot, and yeah, hope you have questions, and I can answer some of them, yeah.